Hello and welcome everyone. Myself Professor Ashok Thumar, and I am working in Department of Mechanical Engineering at Dr. Subhash Technical Campus. Today we are going to discuss remaining portion of chapter number 3, that is velocity and acceleration analysis part 3. Up to now this is the third and last video lecture on chapter velocity and acceleration analysis. Up to now we have discussed about various methods which are being used for the determination of velocity and analysis, and of course acceleration analysis of various point on various link of mechanism. That methods include relative velocity and relative acceleration method, instantaneous center method, Klein construction is there. Of course the remaining portion of Klein construction that we are going to discuss within this lecture. So after Klein construction we will discuss about the analytical method too. Let's start about the remaining portion of Klein's constructional diagram. So in my previous video lecture, in which especially at the end we have discussed about the Klein's construction procedure in order to calculate the velocity and acceleration of various links, the portion was covered only up to velocity triangle, and the remaining half portion of Klein's construction we will discuss within this video lecture. In that, if you have seen that video lecture, in that particularly we have discussed about velocity diagram or the calculation of component of velocity during the or any power or motion transmission. But in this case we will discuss on how to draw an acceleration diagram by using Klein's constructional procedure. So look at the diagram. First you have given again there is a mechanism which is used in IC engine, that means slider crank mechanism that you have given, and there are few steps that you have to follow while you are drawing acceleration diagram. So let's see one by one that step, and accordingly we are drawing Klein's acceleration diagram. First step is to draw a configuration diagram of slider crank mechanism. That means this diagram accordingly you have given some specific dimension like connecting rod, crank, the angular displacement of crank. Accordingly that geometrical dimension, first of all you have to draw a configuration diagram by taking some suitable scale. And then second step again you have to draw a Klein's velocity diagram. As we know that in previous my video lecture we have learned how to draw a velocity diagram by using Klein's construction method. So second step towards while you are doing acceleration diagram, second step is to draw the velocity triangle. Third one is now draw a circle with C as the center and CM as the radius. So just you have to take center C and radius CM and draw a circle CM in that manner. So third step is to draw a circle which having the CM as a radius. After that draw one more circle with PC as a diameter. That means you have to draw the circle in which specially PC has the diameter, so your circle will look like that. And if you are drawing a circle PC, of course this circle will intersect at 2 points, point N on PO, that means point N on PO over here, and point Q on PC, that means point Q over here. This is two intersecting point whenever you are drawing the big or large circle PC. Now if you are carefully looking this two circle and joining this both of the intersecting point along with the crank, this, so ultimately it will become look like we can say that quadrilateral, and quadrilateral CON and Q, that will become a quadrilateral by drawing both of the circle and joining the intersecting point with crank. Now basically this quadrilateral is the kind of we can say that the acceleration, Clench acceleration diagram. Now again what we have done in case of Clench velocity diagram, herein also we have to compare this acceleration diagram OCQN with the acceleration diagram of relative acceleration procedure through which we have drawn acceleration diagram too. So right hand side over here, this diagram is drawn, vector diagram is drawn by using relative acceleration method. So now it's time to have the comparison of both of the diagram drawn by Clench construction and relative acceleration method. Now concentrate over the diagram drawn through relative acceleration diagram OC XP. Focus upon this acceleration diagram, in which specially small OC represent FCO, and which is parallel to line OC, that means this line. Again if you are comparing CX vector, that means vector CX that over here, it will represent the component of acceleration FPC, and which is coincident with the geometrical dimension of a 4-bar chain mechanism CQ, that means this. Again XP, that means XP which represent the acceleration component, actually tangential acceleration component FTPC, and which coincident with the geometrical dimension QN, that means this link, or we can say that it represent or nearly equivalent with the QN vector of Clench acceleration diagram. Again we can say that OP, that is represents the acceleration of a piston, that means over here, and it coincident or coincide with the NO, that means this is NO, and this vector is taken from by drawing Clench acceleration diagram. So we can say that all that NO and OP and all other remaining OC, CX, XP are truly equivalent to that of the vector drawn by using Clench acceleration procedure. Now we can compare both of the acceleration diagram, and by taking the ratio of that particular acceleration diagram, ultimately small OC upon capital OC, that will be equal to small CX upon CQ is equal to XP upon QN is equal to CP upon CN is equal to OP upon NO, and that is always equal to square of angular velocity. One more thing, look at the terms, or we can say that the vector we have taken OC. Of course OC is nearly equivalent with that of the capital OC of that particular Clench acceleration diagram. Similarly, you can take any vector like small OP, that means small OP, and of course this is small OP, and which is truly coincident with the vector NO. So this is true, and you can take any ratio which should be related with both of the acceleration diagram or vector diagram, and it will be always equal to omega square. Now by putting the values of OC, CX vector, XP, CP and OP in subsequent steps, so ultimately you are getting FCO upon OC is equal to FPC upon CQ, that is equal to FPC upon QN is equal to FPC upon CN, that is equal to FP upon NO, and that is equal to omega square. Over here we know that T stands for the tangential component of acceleration, and whereas C stands for the centrifugal component of acceleration. So this is how you can have the comparison and simplification of both of the acceleration diagram. Now from the above relation, you can easily convert all the acceleration component like FCO, centripetal component, that should be equal to omega square into OC. FPC should be equal to omega square into CQ, FPC that is equal to omega square into QN, FPC that is equal to omega square into CN, and finally FP, that means the component of acceleration of a piston, that is equal to omega square into NO. Now, in which suppose you required to calculate the acceleration of any component which is located at any arbitrary distance on a connecting rod PC, then it is easily to calculate the acceleration of that point X by using Planck's velocity, or we can say that Planck's acceleration diagram. Just you have to take ratio in such a way that Cx upon Cp, that means you have to take Cx upon entire length Cp, and that should be always equal to the small that means Cx upon Cn. If you are satisfying this condition, you can put the relation like Cx upon Cp, that is equal to Cx upon Cn. Now you can easily convert the above equation in terms of Cx, and that will become Cx is equal to Cn into Cx upon Cp. So finally your equation that you required for the acceleration calculation, Cx will be replaced by Fx, that means the component of acceleration of a point X, and that will be we can say that it will be represented by omega square into Ox. So this is how we can have the drawing of the acceleration diagram by using Planck's construction method, and you can compare both of that taking the coincide link vector ratio, simplify it, you will have the acceleration of each and every component of the link that you have given in Schreider-Crank mechanism. Now point number 2, that is analytical method. Actually, up to now we have discussed numbers of the method through which we can calculate or determine velocity and acceleration component, like relative velocity and acceleration method. Planck construction is there, instantaneous center method is also there. Of course, few still more graphical method is also available, but subject point of view, this is more than enough. And now we are going to discuss the second procedure through which you can also calculate the component of acceleration and velocity of any kind of mechanism that you have given, and you can analyze the mechanism and links to. So this is the analytical method through which you can calculate the velocity and acceleration component. Generally, this analytical method is used to find out the velocity and acceleration of various parts of especially IC engine. Look at the diagram. You have given an IC engine mechanism with OC is the crank and CP is the connecting rod. Now think that the crank rotates with an angular velocity of omega radian per second, and crank turns to an angle theta from inner dead center. Before having a relation of velocity and acceleration, let assume that the R is equal to crank radius, L that is equal to length of connecting rod, small n that stands for the oblique ratio, that means L by R, theta is equal to angle turned by crank from inner dead center in clockwise direction, omega that is the angular velocity of crank, and phi that is the angle of inclination of connecting rod with line of stroke. Whereas x suffix p, that is a displacement of piston from IDC to BDC, that means inner dead center to bottom dead center, and Vp that stands for the velocity of piston, and Fp that is acceleration of piston. Now one by one we are going to derive the relation for the various component for the IC engine mechanism. First, that is the displacement of piston. When crank moves from inner dead center to outer dead center through an angle theta, from IDC, that means inner dead center, then the displacement of piston is given by very famous equation, that is xp is equal to p1p, and that is equal to op1 minus op. So ultimately, by putting a relevant value of op1 and op, you will have L plus r minus r cos theta plus L cos phi. Further simplification of this displacement of piston relation will give us a new relation like r bracket 1 minus cos theta plus L bracket 1 minus cos phi. Now from the figure we can derive relation of Cn, and that is equal to Cn is equal to r sin theta, and that is of course equal to L sin phi. Look at the previous screen. That Cn can be evaluated by considering this triangle, and of course you can also have the value of Cn by considering this triangle. So by using trigonometric relation, you can have the Cn is equal to r sin theta, of course is equal to L sin phi too. So again sin phi will becomes r upon L sin theta, and we know that r by L, or we can say that L by r, that is equal to n. So ultimately relation for sin phi will become sin theta upon n, and we know that the relation for Pythagoras theorem, that is sin square phi plus cos square phi, that is equal to 1. So from that you can have the cos phi is equal to under root 1 minus sin square phi. Again sin phi can be replaced with sin square theta upon n square. So just you have to put the values of sin theta upon n, and you have to replace sin square phi in, so that you will have the cos phi is equal to 1 minus sin square theta upon n square. So by taking LCM, simply you will have at the end the cos phi is equal to under root n square minus sin square theta upon n. So putting that all that values of sin phi and cos phi into the basic equation of displacement of piston, you will have r bracket 1 minus cos theta plus L bracket 1 minus under root n square minus sin square theta upon n. And if you are simplify that relation, ultimately you are getting r 1 minus cos theta plus n into r bracket 1 minus n square minus sin square theta upon n. Still you are taking LCM of n and simplifying that relation, you will have xp is equal to r bracket 1 minus cos theta plus r bracket n minus under root n square minus sin square theta. So this is the relation through which you can calculate analytically displacement of an IC engine mechanism by using relation of xp. Similarly, you can also have calculate velocity of piston by using simply the basic mathematical relation, that is the rate of change of displacement with respect to time, and by putting the values you will have d upon d theta into d theta upon dt with respect to xp. So ultimately you are getting that omega into d theta upon d theta into xp. So by simplifying it, the velocity of piston will become v suffix p, and that is equal to omega into d upon d theta. By putting the values of xp in this place, you just find the finally velocity of piston, that will become vp is equal to omega into r upon d theta 1 minus cos theta plus n minus under root n square minus sin square theta. And after differentiating, you are getting the final relation for the Vp, that is equal to omega into r bracket sin theta plus sin 2 theta upon 2 under root n square minus sin square theta. But we know that length of the connecting rod is more than that of the radius of crank, so of course L by r, or we can say that the oblique ratio n is always greater than 1. So ultimately your equation will become v suffix p, that means velocity of piston is equal to omega into r bracket sin theta plus sin 2 theta upon 2n. So this is the equation for the determination of velocity of piston. Similarly, you can also determine the acceleration of piston, like just you have to put the values of the velocity in equation, acceleration equation. So over here, just by put the values of Vp that we have already derived in previous relation. So by putting that value, ultimately you are getting the final relation like omega into d upon d theta bracket omega into r sin theta plus sin 2 theta upon 2n. Further simplification will give us a new relation that is the acceleration of piston, that will be equal to omega square into r cos theta plus cos 2 theta upon 2n into 2. And so that omega square into r cos theta plus cos 2 theta upon n will be the relation for the acceleration component of with the piston. Now after that, if you still wish to have the modify or simplify the relation, then the acceleration will become omega into d by d theta omega r into sin theta plus sin 2 theta upon 2n. So in that particular relation, the value of Vp, that means this value of Vp is substituted over here, and by simplifying that the relation or the equation, you are getting W into R d upon d theta omega bracket sin theta plus sin 2 theta upon 2n. Further simplification if you are taking, then it will become omega into R bracket omega into cos theta plus 2 cos theta 2 theta upon 2n plus sin theta plus sin 2 theta upon 2n d omega upon d theta. And pre-final equation that will become convert like omega into r omega cos theta plus cos 2 theta upon n plus alpha upon omega bracket sin theta plus sin 2 theta upon 2, and this is possible by putting the values that the d omega upon d theta is replaced by d omega upon dt and dt upon d theta. So finally equation of the acceleration component of piston will be omega square into r bracket cos theta plus cos 2 theta upon n plus r into alpha bracket sin theta plus sin 2 theta upon 2n. So this was the analysis of piston alone, in which we have derived the relation for displacement, velocity and acceleration. Similarly, you can have the velocity and acceleration derivation for the connecting rod. From the figure we can write like a trigonometric relation in that way, that the sin phi is equal to sin theta upon n, and by differentiating this relation you will have d by dt sin phi is equal to d by dt sin theta upon n. So you are getting that d upon d theta into d upon d phi into d phi upon dt into sin phi is equal to d upon d theta into d theta upon dt sin theta upon n. Over here there is a multiplication and dividing this equation with d5 and d theta on left and right hand side respectively. So by solving that you will have cos 5 into d5 into upon dt is equal to cos theta upon n into d theta upon dt. Now we know that the d theta upon dt, that will be the omega angular velocity of crank, and of course d5 upon dt, that is the omega suffix pc, that is angular velocity of connecting rod. So by putting both of that value into the above relation, you are getting that cos 5 into omega pc is equal to cos theta upon n into omega. So convert this relation in terms of omega pc, that means angular velocity of connecting rod, you will have omega cos theta upon n cos 5. Still you can simplify it like omega pc is equal to omega cos theta, and n cos phi is replaced herein by n under root n square minus sin square theta upon n. By solving that relation you will have omega cos theta upon n square minus sin square theta. So this is the relation for we can say that the velocity component of connecting rod. Similarly, you can have the angular acceleration component of connecting rod by just simply putting the values of omega pc over here. So ultimately the relation will become d by d theta bracket omega cos theta upon n d theta upon dt, and again by simplifying it, it will give us a new relation like omega d upon d theta omega cos theta upon n, because we know that d theta upon dt, that will be the rate of change of displacement with respect to time, and that is the angular velocity omega. So over here d upon d theta is replaced with respect to replaced by the omega. Now again alpha suffix pc, that means the angular acceleration of connecting rod will becomes omega into omega, that becomes omega square upon n minus sin theta. So alpha pc, that will be ultimately becomes minus omega square upon n into sin theta. Now just you have to again you can also derive the relation for the angular acceleration of connecting rod by putting the values of the angular velocity in this bracket. So you can have the other option to finding out angular acceleration component. By putting the values over here and differentiating that relation, you can have the relation like omega upon n in bracket omega minus sin theta plus cos theta into d omega upon d theta. Again, by simplifying that relation, you can have omega upon n minus omega sin theta plus alpha upon omega into cos theta, because we know that rate of change of angular velocity with respect to angular displacement, that will always becomes the ratio of angular acceleration and angular velocity. So ultimately by doing so and simplifying that, you will have at the end acceleration of connecting rod will becomes alpha pc, and that is equal to minus omega square upon n into sin theta plus alpha upon n into cos theta. So dear student, this was the analytical method in which we have specially focused upon piston and connecting rod. We have calculated the velocity, displacement and acceleration component of especially piston, and as well we have also calculated velocity and acceleration component of connecting rod 2. In that way, you can also calculate and derive the relation for connecting rod 2, or we can say that the other links that are being mounted on we can say that IC engine mechanism. By adopting same procedure, same mathematical relation, by using trigonometric relation, you can derive the relation for the velocity and acceleration for other link too. Thank you very much for your kind of attendance to my video lecture. Thank you very much.